Okay, welcome guys. Welcome to today's stream, 26th August. I'm trying to start early, as soon as possible. So let me check my audio. Okay, it seems fine. Audio is fine. Internet is fine. Okay, the connection is good. 0 viewers. Chat rate is none. Concurrent viewers. Okay, good. Let's get started. Okay, you can see my screen. We activate Tmax. What? It's activated already. Oh. Wait. What I have in here? What is this? Oh, really? Okay, we have 3 files. Okay, look. Okay, so let's just close this. Okay. So let's go to the main quickly. Okay. We use CV to import to visualize NumPy. I don't know. TinyGrad. Yes, I need to use OptiGrad. Okay, we have a dataset, and then we have a generator. Okay. Our generator is very simple. Linear layer, ReLU. Linear layer, ReLU. Linear ReLU. Linear layer. And then reshape. What about if I just use leaky ReLU? Okay, I don't see any other problem here. Okay, good. There is difference between leaky ReLU and ReLU. Okay, that's a generator. Then we have a discriminator. Okay, fine. I mean, this is a borderline where everything is like looks fine. Above, fine. Below, not fine. Below something important. Okay. Srajal Astana. Okay, welcome. Today we are debugging our yesterday's GAN model, and we have a time limit, so we should hurry up. Okay. We need to train. So in order to train this GAN model, we need to provide them the, we need to allow the models to interact with each other, and they should grow together. So if they grow together, they will work fine. If they don't grow together, they doesn't work. They don't work. So for example, if generator generates very realistic images from if we allow generator to train for a long time, the generator will generate so many good images. And if we don't allow discriminator to train to a certain extent, as we allow it to this generator, this guy will suck. This guy will not train or not follow this generator rule. So if it doesn't follow generator, then it is wrong. It is damaged. It means our chain is broken. So what we should do in GAN model is that the speed of training for both models should be equal, so that none of these should be stronger or weaker. They should be together. So in initialization step, of course, they have random values, right, in their weights. So as they update their gradients, we want them to grow together. Bro, are you make some stuff related to LLM, or do you want LLM stuff? I can do LLMs, but what do you want exactly? We can do LLMs, of course. I will do LLMs also. Okay. So, so this is script for training. Okay. I initialize discriminator and generator. I make a optimizer. Page size 64. Okay. Number of steps. I just initialize as 5, and then this is our core idea, core logic. Okay. So if you want LLM, just write what LLM you want, or what do you want to train GPT-3, GPT-4, or what? I'm curious. So write what do you want, or what you are not understanding, or what do you want to prove. We have total loss. Okay, now we are training the what? G. We are training discriminator first, and then generating. What? Okay, 1, 2, 3. Right. Bad. It's bad. It is not total loss actually. It's bad. It's bad. Total generate total discriminated loss. Training generator, okay? Generator, okay? GANs are easy, but they are not super easy, so therefore it's a bit tricky. Training discriminator. It all depends on your faith, okay? That's our how can I say? That's our motto, not motto. That's our best word, quote, slogan. No, slogan is not good. Motto. Okay. Or best or What is synonym for motto? No, it's not motto. It is, quote of the day. Maxim. Yes, it is maxim. It is maxim of the day, okay? Guys. Not this one, not this one. Okay, this one. It is maxim of the day, okay? Maxim. It all depends on your faith, okay? So we need to train discriminator first. We have to train discriminator first. For train discriminator, we need two things: original X dataset and fake dataset. So fake dataset can be obtained from the generator. Then DLOS. Okay, it is from train discriminators. This is just basic stuff. Okay, train discriminator. Let's go to train discriminator stuff. Let's go to the function train discriminator. So we have X. It's fake. X. It's also tensor. Tensor. Okay. We initialize 0 grad. We can do it now. We can do it a bit later. Input X. It's useless. Then Y is equal to tensor dot zeros page size and 2. Okay. Yes, shape is like that. Y1 is equal to torch 1s, torch 0s, and torch concatenate. Okay. Okay. There was a way. No. So I wanted actually, basically what I wanted is that let's say I have a matrix M and it has a 64 to 2 dimension, okay? So when I have this matrix, it's all zeros, okay? It's all 0, 0, 0, 0, 0, 64. Two columns, 64 rows. So I want them first row should all have a 1 value, and the second column should be 0. So I was thinking like M, like in tensor, like in pandas. Let's say like all, and then first column equal to 1. I was thinking like if I do like this, it should work, but it didn't work. Unfortunately, it didn't work. So I need to find another way. So from tinygrad import tensor. Okay, we have a tensor. So let's say we have a, so I have another approach. I say y once. No, wait. So tensor zeros. NumPy. If I do NumPy, I can see it. Okay, see? Okay. So I have a tensor zeros. So I can do tensor. Okay. So concatenate. What? Concatenate tensor dot ones 64 tensors zeros 64. Okay, it's concatenating in one direction. Okay, I don't want like that. 64 and 1. 64 and 1. Okay. Dimension equal to 1. Okay. Got NumPy. That's what I want. So now we proved it. So we can use this logic. So what is that? This one. Yes, page size. But actually it should not be page size. Okay, it turns out we need to add another dimension. and then we need to say tensor concatenate. Yes, correct. And then ones, zeros, and then dimension equal to 1. Yes, correct. We don't have input variable. We have what? We have what do you want to input first? Let's see. Let's do the x, okay? Original x, and we have results, right? And we have a step, it means we update the gradient. Do you think this is a good approach? Should we update now? Because I have a concern. Let's write it. Concerns. If I update twice in each frame, the gradients of discriminator, it might be stronger than generic. What if we update params only once? Okay, I wrote my concern. It's good. It's a good approach to write. Then fake. Oh, I don't like this word. Fake. Fake rest. Oh no. Because fake x comes to the d. And then fake loss. Fake result multiplied by fake y. What mean? Fake loss dot backward. And then we do step. I'm doing step only one step here, okay? I don't want to update twice. So now we don't have a fake y initializer. So what is this? Just guys, yes, guys. It's tensor. It's tensor, and we concatenate. But here we will say y zeros and y ones. Dimension equal to 1. Okay, awesome. How beautiful this code looks. Except this concern. Return loss. Return loss? No, guys. Return loss. Loss. Fake. Loss. Should I do like that? Summing up is maybe bad idea. Sometimes it might be a good idea. Let's see. Maybe summing might be a bad. Yeah. Now looks fine, right? Looks fine. Do you have any bugs? Fake x. We have a fake x. Okay. X, y, zeros, d. Okay. Initialization backward. Result y. I'm not sure whether this will work or not. So let's go to the second one. Okay. Let's exit this. Is this this Python. So now Python.main. If I do main, it will go to discriminator and train, and it will go to the debugger mode. Okay, we have a debugger mode. So now we have a result, right? It's 64 by 2. Okay. I want to see the actual result. So please be patient. Okay, it is very small numbers. It is negative values also. There are, yeah, almost all are negative. Makes sense. And then we want, what do we want to do? We want the result multiply with what? With y, right? Oh, why our y is in this shape? It's bad because our y should be tensor concatenate dimension, page size. Actually, y should not be, no. Actually, y should be 64 by 2. Let's see. So tensor concatenate. So I say y ones, y zeros, dimension equal to 1. Shape. Index error. Dimension 1 is out of range. Just wait. Y1's shape. See. We have a problem here. Tensor 1's 64 1 shape. What? Okay. Shape. Makes sense. But why our y is doing this strange thing? Wait. Why it's 64? Wait. I see. It's because, guys, it's because we didn't save it. Now we save it. Now we can do like this, and we can check the result, check the y shape. Oh no. Again, the y ones. Oh, I don't know. Because in this logic, it should work, right? You see? We are in another place here. You know where I need to go? Need to go to Tafakkur. What is that? Oh my god. Naqshli Bishik. Okay, now we are here. Python main.py. Okay. Now see, we are correct. Now we are in right direction. Okay. Let's dot shape, y dot shape. Okay, we have this kind of shape. Okay. Bro, what project are you working on? It is GAN model. GAN. Generating images. I want to generate images. So now we need to multiply. And then get a mean. seems it will work. It seems it works. So this is our loss function, you know. We just take the result output from the discriminator and multiply with y. And then we get a mean of that. And then we go backward. Why GANs are important architecture in AI? Because they are they are like they start the new generative AI field. They opened that field, and they use very smart idea of using two models. Usually in conventional AI, people use only one model, but here they are using two models together. So that was also important step in GANs model. Okay, so I have this loss function. So result is output from Tangeness activation, and then also from log softmax, if I don't mistake. Oh, wait. Discriminator is output from log softmax. So what is the formula for softmax? Softmax is softmax. It was like k divided by sum of k. K is where it is a number of element, value in the array or in the vector. No, I make mistake. No, it should. It was something different. Softmax. We have sigmoid. Sometimes people forget. I also forget these formulas. Sigmoid is what? Sigmoid is it divides the coming input to the two things, whether 0 or 1. It tries to split this difference. So for that they use what? 1 plus something, 1 plus, or it was like k power something. Okay, we need to check. We will check it. So, but before we have a log softmax, and then we have a log softmax. If someone found it, the formula, or have a idea, if you already know it, please don't share, but share hints, okay? Or if you don't know, don't hold back and write on chat. What do you think? Okay, we have a result, and we want to clarify y. Our y is 64 columns, where we have ones and zeros. Okay. Our loss looks fine. Fake one. Okay. I'm not sure, but train discriminator looks fine. For now, I don't see any anomaly stuff here. Maybe fine. Okay, then let's go to generator, because we need to also generate stuff. 0 grad fake y. Generator is G, noise. We have a noise. We generate images, okay. And we pass the generated images to the discriminator while we are squeezing. It's extra work. Then we have a loss, right? I like this kind of process. This is good. So now the discriminator output is two-dimensional. So fake y should be two-dimensional. So here generator should try to generate images in such a way that discriminator cannot differentiate. So it means our y is equal to tensor dot concatenate tensor dot ones fetch size 1 and tensor, and then zeros. Oh, zeros. Okay, no, guys, zeros fetch size. Size 1 and 1 dimension 1. Okay, this is our y. I don't need it. Generated images. Okay, discriminator is used for checking the loss. Squeeze. I don't like this squeeze, guys. This squeeze is ugly. Squeeze stuff. Now. Okay. Import. What do I import? Import Python debugger. Oh, why we need debugger here? It's simple because we can do it interactively. Trace. One typo. Trace. Set trace. Okay, log. Okay. I don't need it. Step, generator step. We will update the generator and return the loss. Okay. I don't need it. Image write GAN generated. Okay. I don't have any arguments for it. So now if I run it, first we will go to training the discriminator for 5 steps. Okay. pdb dot. Okay. It happens. Bugs are always happens, even if you are the best developer. Oh. Yep. Okay, we have discriminator stuff. We want to go only one step forward. Okay. Oh no. We want to go next. So like this. Okay. If I press S, it will go to the next one. If I press N, it will go to the next one. We are inside the tensor. No. Let's go just to the second one. Okay, it's taking a long time. Okay, then continue. 3, 4, 5. Oh my god, we have a problem. Where in train generator, when we are concatenating, we didn't mention 1. What is 1? It's saying what do you do? What is 1? Okay. So the problem happens here, as I understood, is because of this guy 1. Okay. Oh. What? Because I didn't say dimension equal to 1. It turns out I need to explicitly mention it. Let's train. Continue. One step. Second step, third step, fourth, fifth. Okay, now we are in generator. Okay, finally. Okay. Because total discriminator loss. Oh, see, our loss is becoming so big, increasing. It's bad. It's like -1, -1,000, -8,000, -30,000, -75,000, etc. So now we have a fake y. Ah, see, I didn't say fake y. See. Guys, if you see the touch this kind of mistake by me, just write. I will fix it. Sometimes I also forget. Generated images, discriminator key. Okay, discriminator. Shape is like that, and we do with y. And then we get the result, and I'm saying just get the mean value. And to check the mean value, we use numpy. Okay, -0.28. Okay, -0.28 loss, and then backward we update the gradient, and then we do a step, and then return the loss, and then the loss will be written to the total G loss, and we will do range n step. N step is equal to the 5. Then we save the total G, and then for debugging purposes we will write it to here, and then we generate the image. Okay, maybe generating images now, maybe it's not necessary. Looks like not necessary. Anyway, Q Python exit. Continue. Okay, that's our loss. Maybe I should put minus before. Continue. Okay, now we are done. Look, the G loss is 0. G loss is increasing. Wait, bad. That's bad. That's bad. I think our loss should have -1. Because for discriminator we are doing twice. I don't like that. Twice. Backward and then backward, and here we are not cleaning these gradients. So we have actual gradients here, and we do the one more time, and then we are writing again to that. We are not writing. We are accumulating the existing gradients, because we do backward and we have existing gradients, and we do twice, we have another big gradient. So I don't want to say, but we need to do update. We need to do step here also. Turns out, okay, -1, and here -1, +1 star. Okay, good. Okay, we write it, yes. So now, okay, wait. I want to get rid of this one. Why? Because for now I don't want it to be there, but I want it to be here. Okay, let's go. Let's get started. Okay, that's our loss. Okay, good. Okay, it's as a program basically saying me, do you want me to execute generated images equal to generator tensor random 1 to 256? I will say continue. Our loss is increasing. I don't know, let's go. Whoa. Oh, D becomes 0. Generator increases. No, guys, don't be like that. Okay, we have 3 viewers, congratulations. I am curious. Total D loss. It's all minus 0, 0, 0. Okay. Total generated loss. Okay. Let's. Means it's stuck. Our model stuck somewhere. Can I see the images? Let's look to the images. Let's do the sort by what? Data created. Fun. Again, actually basic. And then again. Do you want to see image? Here it is. Total black. Means all 0. That's not good. Okay, anyway, we have a progress, okay? Git status. Yep, of course. Git difference made. Okay, we do change. We change the value to leaky value, and then log softmax, and then we update it. Okay. Train. You know, I think legitimately, I think I need to reduce the number of steps. معلي عشان تكون ده شو صار. اشتم. مالك؟ Okay, that's our D loss now. Total generated. Let's see D loss first. Our goal is that their loss should be almost same. I mean, in same threshold, in same range. Okay, in same range. Okay, I need to turn off this. Yes, that's right. Now it's more peaceful, right? Now you can hear more, right? Because my fan was on. Okay, now better. Okay, let's continue. Now our generator loss is 0. Why? And discriminator is 36. Maybe it's because of learning range. A learning rate is big. Okay. something wrong. Why my all images are black? Look, one step. Oh. Generated image, right? Shape. Okay. I want to see the first generated image. Yes, I want to permute. So now it will be what? 1, 2, 0. Okay. Actually, I don't need anything like permute, etc., because it's just gray image. Okay, good. I want to see it as numpy. Okay, it's not black. It's because just we have a normalized image. If I do 255, and then it will be open CV or classical image. Okay. How ugly this code looks like. NumPy. Now, before calling NumPy, we need to unnormalize it. Bro, what are you doing? Make sense? Okay. Let's go. It is 6:47 a.m. and it is raining day today. Alhamdulillah. Okay, now you can see image, okay? It is okay, look, okay, guys. Black means 0, okay? 255 means white. If you see here a lot of white images, white pixels, it means they are all 255 or closer to 255. Okay. If you see black images, they are small images. Their value is around 0. Next step. 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 Okay, it's not doing anything. I have something very fundamental problem here. I say the problem might be in learning rate, so maybe let's reduce to 0.3. Another good approach is to do good normalization, a good initialization. Because now it's all black, kind of black. Because guys, it is obvious because our n step is so small. This one, you see this one, okay? Can you see it? This one has a bigger number. Okay. Nine hundred steps. It takes time. Can we improve, optimize it? Why I'm doing detach? Okay. We need to wait. Maybe it was bad idea to use all 937 steps. Maybe it would be good to use maybe like 100 steps to see the scalability. I don't like this kind of waitings. It is bad. It means there is something wrong. Because you lose your time. It's my time. It's our time. Oh wait, I cannot do just wait, guys. The noise or images are normalized. Tensor random 1 to 2 5 6, does it has a range of -1 to 1? That's a good question. Oh, what is this? Oh, look, from tiny grad import tensor, okay, tensor dot rand n 1 2 5 6 shape. Oh my god. No, we don't want this. We don't want. Never. Random tensor. Rand integer. I want to give a range, okay, to you. You need to have a range. No, it makes it so three-dimensional. Tiny grad tensor. Concatenate. Oh, what are you looking for? Okay, I'm just looking for, you know, I'm just looking for rand n. We have. Can you see this one? No. I am working on a unique GAN model and struggling with the parameter tuning as we speak. Yes. What kind of special GAN are you working on? So now here I need to give uniform. Maybe we should use uniform, guys. Maybe. Tensor dot uniform. What? I mean, what is the parameters for the uniform? Uniform. Shape, okay, low, high. UVC GAN. UVC GANs. Guys, let's have some break and check what is UVC GAN. Image to image style transformation based on cycle GAN. Cycle GANs. Okay, it has a combined hybrid generator architecture, UNet VIT, and self-supervised pre-training. Oh, okay, I see. Asymmetric cycle GAN, so we can apply it to the data domain with opposite shapes. We are using this model with original creators to apply to hyperspectral datasets. Okay, asymmetric cycle GAN. Yes, that's new for me. I like this one. So it's image into image model where it is trying to change the style, and it has special functions, special architecture. So it has a hybrid generator transformer stuff, unit stuff, and it has a cycle GAN based on the cycle GAN. I'm working on simple model, guy. I'm working on very basic GAN model. I am doing very basic stuff. So I'm training the MNIST GAN model. So and here I need to edit it. Uniform. What should I give uniform? Tensor.uniform. I like these UVC GANs. I want to try them. So first, I need to debug and fix this problem. So tensor.uniform, I can give uniform, but the logic but it doesn't make sense. That minus 1, 0, low, high, 1. Okay. Yank. Test. This is our noise, okay, guys? This is our noise. YouTube algo recommended you on one of my relative Flash accounts. Google pinned me down, well, I guess X. Welcome. That's good. Then, if you have like, it seems you understand better than me the GAN models. So if you have ideas or if you have recommendations, please give recommendation. I will definitely apply to the code. Noise, tensor rendered, page size. Page size is 1. Here's page size. And I'm not using the TensorFlow. I'm not using TensorFlow torch here. Generated image. Fine. Okay. So this is our noise. Before, noise was generated only by this guy. That was stupid. Why I am doing this detach? I don't like this detach. Oh, steps, guys. Steps. Ugly steps. No, we don't need the steps. I want steps to be small. Let's say 100. Okay. Python. Me. Okay. I started with TensorFlow but ran into 2-minute compatibility issues. Also found out most people use Torch now, and anyway, so stuck with that since. Yeah, nowadays people just go with Torch. I see so many repo with Torch. TensorFlow, so not that much, because they grow so big. They are gigantic frameworks. Is both Torch and TensorFlow. So total, I want to read the paper that UEC GANs and try to apply. So total, the loss like this. Okay. Look, our D loss is decreasing, right? You can see it, it's decreasing. It starts from 3, it goes to 0 0.00003. Okay, loss is, it means our discriminator knows what is true, what is fake. It means that. So now I want to see total generator loss. It is 3100000. Okay, it means it also knows something. Interesting, it also knows something. So now continue. It means it writes to this one. Okay, this is image, okay guys. This is image generated. Looks fine. Looks fine. Let's go. UVC GANs. So we will add this UVC GAN to our maximum of today. Okay, today's maximum. Just guys, let me to bring some milks. Milk. We need to drink milk. Milk refresh people. Milk refresh mind. Milk gives energy. Cycle GAN is a good start as well, since it's way to unsupervised translation. The goal from this project, just to learn, just to discover something. So because it was like dream, you know, I wanted to build GAN. This is simple GAN. It's when I was in school. So I'm doing now. Now I have some time, so I want to do it. So then cycle GAN, yes. I know I need to do cycle GAN. We have a diffusion models. Diffusion's also another generative AI. Another domain, not domain, let's say another approach to generative AI rather than using this GAN architecture. Okay guys, it is training and you can see there is some kind of digits, okay, no? Some kind of digits. If you cannot see, maybe I can make it bigger. Icon as gallery. Maybe this is 2. So I think the model is working quite nice, quite good. But problem arises because I am doing it manually each time, right? Using this one. I want to ignore it, and a number of steps should be original, and then I want here a small log print. training. What? Training generator. What time is it in your region, in your area? Print training. What is this? Discriminator. Discriminator. Let's go. Let's go. 7:10. 7:10. Because today I have work. I have a work, and at work I have another project. You know. At work it is more like computer vision project. Cycle GANs. Cycle GANs. When? Who actually introduced cycle GAN? Cycle GAN. No paper. Oh, maybe this one. UVCC GAN. Okay, UVC GAN. It is UVC GAN. Cycle GAN. PDF. Archive. PDF. Cycle GAN, a master of steganography. Adversarial attack. Adversarial attack. Let's check the model. No change. Okay, cycle GAN is one recent successful approach to learn transformation between two image distributions. Okay, what does cycle stands for in this GAN model? Okay, it is GAN model. It means it is based on this GAN architecture. It uses generator and discriminator, but it has a cycle. What kind of cycle is it? In a series of experiments, we demonstrate an intriguing property of the model. Cycle GAN learns to hide information about the source image into the images it generates in a nearly imperceptible high frequency signal. Okay, it turns out the cycle GAN learns to hide information in the generated images. Okay. Imperceptible. It means very very invisible, very in very best way. In the best way to write to save information there. Okay. This trick ensures that the generator can recover the original sample. Yes. If it can hide information into the generated images, it means the generator knows something. It learned something. And this trick ensures that the generator can recover the original sample and thus satisfies the cyclic consistency requirement while the generated image remains realistic. We connect this phenomenon with adversarial attacks by viewing cycle GAN's training procedure as training a generator of adversarial examples and demonstrate that the cyclic consistency loss causes cycle GAN to be especially vulnerable to adversarial attack. Cyclic consistency loss. Okay, I don't get this cycle consistency loss. They use adversarial attack adversarial attack is one of the cybersecurity attacks, you know. Adversarial attacks means providing fake images? No, no, no. Adversarial attacks. So what kind of attacks we may have in cybersecurity regarding the AI? For image models, we can provide the image, let's say face of the person, image, let's say 224 face of image, where we have a small change in distribution of the image. So, and if we pass this image to the model, let's say image classification model, that image classification model will, because it is just a matrix multiplication, it will think, so their calculation will turns in such way that it will not be a person, or it might be a cat, or it's something like that. So it means manipulating the model's weight based on the input image. Can we say that adversarial attack? Maybe I am close, maybe I am wrong. That's about cycle GAN. UVC GAN. If we read abstract and if it makes sense, we should read all. Or just scroll down. Oh, cool, cool. Unpaired image to image. Unpaired. Why unpaired? Unpaired image to image translation has broad applications in art, design, and scientific simulations. Okay, this work revisits the classic cycle GAN framework and boosts its performance to outperform more contemporary models without relaxing the cycle consistency constraint. To achieve this, we equip the generator with vision transformer and employ necessary training and regularization techniques. Compared with to previous best performing models, our model performs better and retains strong correlation between the original and translated image. An accompanying ablation study shows that both the gradient penalty and self-supervised pre-training are crucial to the improvement. To promote reproducibility and open source code, the parameter-defined configuration and pre-trained model are available at this link. Okay, interesting, nice. So they took the cycle GAN, they applied these modern techniques to the cycle GAN, and then they provide the results. It's like, there is the A, they take this A, okay, in the literature we have A, let's say A source, or A idea, and we have B idea. So this paper takes A idea, takes B idea, combines, show it, A plus B, good approach. Plus, they say to promote reproducibility and open source. They open source their training, configurations, and etc. So that's good. Guys, maybe should we go and do this one? Guys. But before, let's see our training. Discriminator law 0001, 0001. Okay, it means it learned very well, no? This is the image. This is the image which is generated in first epoch. That is the image generated in first epoch. I have one question, guys. Here we have different digits, right? Look. Maybe you know, maybe I make some kind of mistakes. Look. Now we are giving to the discriminator Are you tracking statistics of your model during training, like the loss value gradients? I'm just checking the mean loss function, mean loss value. Here it is. I'm not tracking the gradients. Do you think we should track the gradients for now? Gradients like the what is the norm value for each gradient for each layer, right? Maybe we should go and do it. But here's the idea. What I want to explain is that we have, let's say, 10 unique values, right? 10 unique digits in the dataset. Yes, we have 10 digits in the dataset, and they are always random. And I want the generator to generate image looking similar to one of these 10 images. Oh, you like making GIFs of your outputs? Oh, that's cute. That's good. Okay, so what we want now? Okay, we want to see the gradients. We can apply gradients to several places. The gradients will help you understand. For example, if you are fluctuating a lot and thus have a too high a learning rate, or if your model is not learning quick enough. Yes, you are right. You are definitely right. You are definitely right. You are right. And we will implement it now. So we can implement here when we are doing step, or we can do it. Okay, let's try to implement here. So in discriminator, we have 1, 2, 3, 4. We have 4 gradient metrics, and you will see references to gradient penalty or clipping in paper which refer to controlling this, basically throttling the learning, so it's more. Yeah, I saw that gradient penalty. I tried yesterday. It was like, in Torch they use this utils dot clip grad value, something like this, and you just pass the model parameters and then the clipping amount. You just controls it. You just control it. So what I can do is that I can say for parameter in the named parameters, maybe if I do like this it may work. So then if p grad is not none, then we can print p dot grad dot norm. Can I do like that? And can I see the name of p? I need a name. Okay, I have a low battery. Go. We are in step training G loss 2. Yes, they are weird. Look, what kind of weird image do we have? And it's not their fault. Okay. I want to check whether this is fine or not. Okay, I want to check it. Okay, if you want to check it, we can do import pdb.set this, and then okay, let's break it down. Set trace. What? Oh, guys, pdb.set trace. I really like this approach. You know, when I was at work and doing the debugging, just import this one, import debugger and set trace, and make it interactive and just debug, as in IPython. Okay, we have a D, and I can say for p in d.named parameters. Wait. Print p. Okay, it doesn't have named parameters. Named parameter? No. It definitely has parameters value. Wait. I have a D, right? Discriminator object, yes. D dot named parameters, named params. It's saying that my discriminator doesn't have. Because it is not torch. Because it's not torch, of course. I like, my mistake is that I stuck with torch. Torch is just a framework. It's not a AI. It's not deep learning. So I can say for layer in d dot layers. Layers is my list, and if is instance, if L is instance of nn, can I call nn? nn dot linear print linear linear, and then L dot shape. No, let's say L dot weight dot grad. Let's check it. So now layers 0 lambda. No. The linear layer dot weight. Okay, we have a weight dot grad. Okay, shape. Okay, good. Grad dot norm. Can I call just norm? What value to drag in grad here? In grad. So grad is a matrix, okay, guys. It is a big matrix. I don't want to show it. I don't want to print it. So it's 1024 to 784. It's a big gradient. So I think a good matrix is just mean value, isn't it? What do you think about it? I can say enumerate and then index, good, and then linear at index. Good. I don't need you. Okay, good. That's good for discriminator. Young. When we do step, I want to print it. Delete it. Insert append. Okay. Wow, it is raining so heavily. It's beautiful outside. It's 7:31. Okay, guys, it's 31. What? No, guys, no. Tank. And then test. And now we are doing the not the discriminator but generator. We just have linear. Everywhere are linears. So now makes sense, good. But here we are tracking at individual step instead of doing general. Or like instead of doing it per epoch, we are doing it per step. So number of steps, I want to make it number of steps small, guys. I mean, what's that small? It's too quick, right? Can you see it? Oh, ugly. If I want to see it, I need to add grad min dot up insert dot item. It is difficult. It is too fast. Why linear layer at 1, at 3, at 5, 0? Oh, look, it is the gradient becomes 0. Our generator works good here. Generator is doing so great. But discriminator, not so well. Okay, now generator has a big loss. Let's leave it as it. Maybe at some degree it will figure out. I will fry some eggs. So generator figure out here is that if there is something in the center of the image, then it is a bonus. Okay, discriminator has very small loss. It means it's doing good job. It means it's doing good job. Now generator has big loss. Okay, generator is learning. Yes, good. I think our approach is now working somehow. I can see a 2. Let it to learn some more time. Oh, maybe for now it's not streaming. Okay. Maybe it's learning, maybe it's not learning, guys. So today's stream is done. Thank you very much for watching. I will leave it as it is. So before dressing up and going work, I will leave it. So let's see if it will work or not. And then I will let you know, inshallah. So tomorrow morning, see you again. Have a productive, good day. Stay positive, and yeah, always stay positive and see positive things in everything. And don't stop learning. Just go. Have a good day. Bye bye.